So good morning everybody. So myself J.V. Aparo, Assistant Professor, Department of Triple E. So today we are going to discuss about Microprocessors and Microcontrollers. So this is the course for Triple E students. So today our topic is discussion about the microcontrollers. So before going to the microcontrollers, first we should know about the difference between microprocessor and microcontroller. So what is meant by microprocessor? So a microprocessor basically a CPU. So that can perform any information, that can perform any task, but to perform this particular task or any task, simply it needs some additional devices or external devices. For example, any RAM or ROM memory, like any other IO ports or any other timers and counter devices like this, some peripheral devices are required. So these peripheral devices are connected externally to the microprocessor. And coming to the microcontroller, so simply it is an integrated chip. So here all these devices like memory, IO ports, timers and counters, so all these be integrated or embedded on a single chip. So this is the major difference between the microprocessor and microcontroller. So to perform any task for the microprocessor based system, it requires all these devices connected externally to the circuit so that it can perform any task. But coming to the microcontroller case, simply it can perform any task, all these are integrated in a single chip. So microprocessor based system very complex because all these devices are connected externally to the system, and this is acting as a general purpose computer. So you can perform any type of task with the help of microprocessor based system. And coming to the microcontroller based system, this is completely designed for performing a specific task only. So it can perform only a specific task, not all the tasks. So this is the major difference between the microprocessor and microcontroller. So coming to the definition of microcontroller, here all the devices, all the components like timers and counters, similarly IO ports, memory devices like RAM and ROM, all these are embedded on a single chip. So this is the definition of the microcontroller. And this figure shows the microcontroller. Here the CPU, so this is the central processing unit. So this is the main part of the microcontroller. So this can perform any type of operation, any type of arithmetic or logical operation. So like this is the brain of the microcontroller. And here the RAM and ROM, these two are the memory components. So RAM is used to store the data memory. Similarly, ROM is used to store the program memory or code memory. So these two are the memory components. And similarly, these are the IO ports, that is input and output ports. So here with the help of these ports, we can give the inputs or we can take the outputs from the microcontroller. So these are the IO ports. And similarly, we have converters also, ADC converter and DAC converter. So analog to digital conversion and simply digital to analog conversion. So here these two are very helpful for microcontroller operation. So here ADC converter will convert any type of analog signal into digital form so that we can give the digital form into the controller. So controller can process the information and gives the output in the form of digital information. Then the digital information coming from the microcontroller can be converted into analog form with the help of DAC converter. So that DAC and ADC, these two are very helpful for the operation of this particular microcontroller. And similarly here the clock generator is also there. So simply this generates the clock pulses to synchronize all the internal operations of a microcontroller. So here all the components are connected or embedded in a single chip, that is the microcontroller. So this is about microcontroller structure. And coming to the types of microcontroller, here the microcontrollers are classified depending on various parameters. The first one is the bits. So how many bits are used? So here the 8-bit microcontroller, 16-bit microcontroller and 32-bit microcontroller. This is the number of bits that can be able to process by the microcontroller. And the second category is based on the memory or devices. So here we have two types, embedded memory, similarly extended memory. The first one is the embedded memory and the second one is the external memory. And based on the instruction set, so depending on the instructions, simply you have two types, RISC and CISC. And coming to the memory architecture, based on the memory architecture, we have two types of architecture. That is, first one is the hardware architecture and second one is the Van Neumann architecture. So we will discuss these things in the later slides. And coming to the first discussion, the first classification is based on the number of bits. So how many bits of information that can be able to process by the microcontroller. So based on this, we can have total three types, 8-bit, 16-bit and 32-bit. So 8-bit means this particular processor can bit 2 power 8. So simply it can process 8 bits of information at a time. That means 1 byte of data can be processed by the microcontroller at a time. So here the range is 2 power 8. So 2 power 8 means 0 to 255. This is the range of 8-bit microcontroller. And coming to the 16-bit microcontroller, so here this particular microcontroller can handle or can operate 16 bits of data at a time. So similarly, the range is 2 power 16. So here it is from 0 to 65535. So this is the range of 16-bit microcontroller from 0 to 65535. And coming to the example cases, here the Intel 8031 and 8051 are the examples of 8-bit microcontrollers. And similarly, the extended version of 8051 comes under the category of 16-bit microcontroller. And coming to the 32-bit microcontroller, here it can process completely 32 bits of information at a time. So this is about the complete classification based on the number of bits. And coming to the next classification, so this is based on the memory type. Here we have two types. The first one is the embedded memory and second one is the external memory. So embedded means simply all the components like IO ports, data memory, program memory, and similarly timers and counters, serial communication ports. So all these are embedded on a single chip. So this is the embedded type microcontroller. So here the 8051 is the example for the embedded type microcontroller. here all these components are embedded on a single chip. And coming to the external memory, so here the IC does not have all the components. For example, it may not have the program memory. So if we take 8031 microcontroller, here the program memory is connected externally to the 8031 microcontroller. So simply the IC of 8031 does not have the program memory. So the program memory is completely connected as an external device. So this is about the external memory microcontroller. So this is the classification based on the memory type. It may be embedded system or external memory system. And coming to the next classification, so this is about the instruction set. The first one is the CISC. So complex instruction set computer, and second one is the RISC, reduced instruction set computer. And coming to the CISC operation, here complex instructions are allowed. So that can perform multiple tasks in one command. So in one command, it can perform multiple tasks, this particular system. And this system will shorten the execution time. The execution time will be reduced by reducing the number of instructions in a program. And coming to the RISC type, here the instructions are completely simplified and using fewer and simpler commands. Here the commands are very fewer commands and simpler commands. So here also we can shorten the execution time by reducing the clock cycles per command or per instruction. So here comparing these two things, basically the RISC offers a better execution performance compared to the CISC. So this is about a comparison. And the next classification is based on the memory architecture. So how the memory is organized. So here we have two types of memory. The first one is the data memory and second one is the program memory. So program memory means it is completely program or code is embedded, stored in the particular memory. So data memory means all the data variables are stored in the data memory. So here coming to the Harvard memory architecture. So in this architecture, both the program memory and data memory has a separate memory. That means program memory can be stored in a single chip as well as data memory can be stored on some other single chip. So simply these two are separately stored in different chips so that we can access these two at a time by using the different buses. So one bus can access the program memory and the other bus can access the data memory. So these two are stored in a separate physical memories. So this is about Harvard memory architecture. And coming to the Van Neumann memory architecture, here we have only one memory chip. The same memory chip can be shared by the both data memory as well as the program memory. So here if we access the program memory or data memory only one at a time. So simply we have only one data bus or one bus. That bus can be used as a data bus or program bus. So simply it can access either data or program. At a time it can access only either data or program. So that it is completely slower as compared with the Harvard architecture. So this is about the based on the memory architecture. And coming to the next topic, this is the architecture of 8051 microcontroller. The figure shows the internal architecture. Here we have a different components. So the major component here is ALU, that is arithmetic logic unit. It can perform any type of operations, any arithmetical operations or logical operations. So basically this is the brain of the microcontroller. And for performing ALU operations, we have two registers, that is temporary registers, TMP1 and TMP2. So these two are the temporary registers. So while performing any operation, if any intermediate result or auxiliary result is generated, that particular auxiliary result is stored in this particular temporary registers. And these two are the main registers. This is ACC and register B. ACC is the accumulator. This is the default register. If we perform any type of operation, the result is defaultly stored in the accumulator. And coming to the register B, this is also used for arithmetical operation, especially for multiplication and division operations. And these are the ports: port 0, port 2, again port 1, port 3. We have total 4 different IO ports are there for giving inputs or for taking outputs. And similarly, we have memory also. This is RAM, and again flash memory, that is ROM. This is the memory. For flash is used for store the program memory or code memory. Similarly, RAM is used to store the data memory. And these are some other additional components. We will discuss these components in the later slides. Here the first one is the CPU, that is the central processing unit. So this is the brain of the microcontroller. So it can process any information or any instruction. Here the CPU contains ALU, accumulator, register B, ESW, alage, similarly temporary registers. So the ALU means arithmetical logic unit. So it can perform any type of arithmetical operations or logical operations. This is the main theme. And coming to the accumulator, this is the main register which is used to arithmetical operations. If any arithmetical operation is performed, the result will be stored in the accumulator default. So coming to the register B, it is used during only multiplication and division operations only. For multiplication or division operation, any borrow or any quotient is generated, reminder, that will be stored in the this particular register, that is register B. And coming to the PSW, that is program status word. So the name itself indicates that it indicates the status of the program. So after execution of any instruction or any program, the result will be stored in the particular destination place. The status of the result will be updated in the PSW register. Here we have different flags, that is carry flag, auxiliary carry flag, parity flag, overflow flag. Like this, we have different flags, flag bits are there. So if any carry is generated in the previous result or in the previous instruction, that particular carry flag will be updated here in this particular register. Similarly, if any parity is there, the parity flag will be updated. So like this, simply this particular register will update the status of each flag, status of the information which is processed by the previous instruction or previous result. And coming to the temporary registers, TMP1 and TMP2, these two are the temporary registers. So here these two will assist the ALU. So while performing any instruction, if any auxiliary result is generated or any intermediate result is generated, that particular result will be temporarily held by these particular registers TMP1 and TMP2. These are the temporary registers which assist the operation of the ALU. And coming to the second one, program counter. So the program counter will store the address of the next instruction which is to be executed. For example, if you have a program which is having 1 to 15 lines, so line 1 to line 50. So initially the program counter will indicate the address of the line 1. So while the CPU processes the line 1 or line 1, then the PC is automatically implemented and it indicates the address of the next instruction, that is line 2. So like this, simply the PC is automatically implemented and it shows the address of the next instruction which is to be executed later. So here, suppose in this program any subroutine is there, any call for subroutine is there, then the PC is automatically shifted to the address or starting address of the subroutine and it executes the subroutine, and after the completion of subroutine, the PCs come back to the main program wherever it left the previously. So simply the program counter will show the instruction of the coming instruction or next instruction. And next one is the memory. This is the flash memory and this is the RAM is data memory. So here the flash memory or program memory, nothing but code memory. This memory is used to store the program or code. So whatever be the program we have written, that should be stored in this particular program memory. And the data is available in this particular RAM memory. Data, variables, operands, all these be stored in this particular data memory. And coming to the stack pointer, so basically this is used for subroutines or interrupts, any calls or interrupts. So here the stack is available at the top of the RAM. So the stack pointer will indicate the top address of the stack and nothing but top of the stack. So stack pointer is a register which is always address the top of the stack. And coming to the next register, this is the data pointer register. So this data pointer register is a 16-bit register. The size of this register is completely 16 bit length. So here this particular register is used to access the external memory. For example, the 8051 already having some internal memory, but that memory may not be sufficient for the program. So we need to connect the external memory to the 8051. So in that case, to access the external memory, so we need some register, that is DPTR, data pointer. So this data pointer will indicate the address of the external memory. So with the help of this particular register, we can access the external memory. And next one is the instruction register and decoder. So from the program memory, after fetching the instruction will be stored in the instruction register, and this particular instruction will be decoded by the decoder and it generates the control signals. So the purpose of decoder is to generate the control signals, so which are in line with the instruction in the instruction register. And the next component is timing and control unit. So this is a very important unit because it generates the timing signals and completely it synchronizes all the internal operations of the microcontroller. So all the internal operation completely synchronized with this particular control signal, that is timing signal. So here all the mission cycles, all the control signals, all the read and write operations, so all these be synchronized with the help of this particular unit, that is timing and control unit. And the next one is the oscillator circuits. So this oscillator circuits generate the clock pulses. So generally we use a crystal oscillator here. So the crystal oscillator will generate some pulses of time, that is clock pulse. So this, based on this clock pulse, the microcontroller the speed will be depends on. So when the clock pulse frequency is more, the speed of operation of the microcontroller is more. So simply the execution speed of microcontroller will depends on the clock frequency of the crystal oscillator. So this is about the oscillator circuit. And coming to the I/O ports. So here we have total 4 I/O ports, port 0, port 1, port 2 and port 3. The purpose of I/O ports is input and output. Simply it can give the input to the microcontroller or it can take the output from the microcontroller. So to connect with the external devices or external peripherals, we use these I/O ports. So here we have total 4 ports, port 0, port 1, port 2 and port 3, and each port having total 8 pins or 8 bits. So port 0 pins are from 0.0 to 0.7. Similarly for port 1 from P1.0 to P1.7. So like this, each port having total 8 bits or 8 pins. So generally the purpose of the main function of all these ports are, so these ports acting as either input port or output port. That is the primary function. So in addition to primary function, some ports having some alternative functions also. For example, if we take the port 0, it can carry address bar data. That means simply it can carry the data as well as the address. So here the size of data bus is 8 bits. Similarly, the size of address bus is 16 bits. So data bus is from D0 to D7. Similarly, address bus is from A0 to A15. Here the port size is completely 8 bits, so it can carry 8 bits of data bus clearly. But coming to the address bus, the address size is 16 bits, but the port size is only 8 bits. So it can carry only lower 8 bits. That means from A0 to A7. So port 0 can carry only lower byte of address bus only, that is A0 to A7. The higher bus, that means A8 to A15. So that will be carried by the port 3. So port 0 will carry the lower byte of address bus as well as port 3 can carry the higher byte of address bus. And port 1 does not have any other function, it only general purpose IO function only. That means it can perform only IO function, that is the primary function, no any other alternative functions are there. And coming to the port 3, it has some special function, that is receive data, transmit data, similarly interrupts. So these are the external functions, that is receiving data or transmitting data or any acceptance of interrupts. So all these functions are alternative functions which are performed by the port 3. So this is about the ports. Completely we have 4 ports, port 0, port 1, port 2 and port 3, each having 8 bits. So all these ports acting as general purpose IO port, that is the function of each port. And in addition to general function or primary function, it has some other function or alternative functions. So port 0 can carry data information D0 to D7. Similarly, address information A0 to A7, that is only lower byte of address bus only. The higher byte of address bus can carry by the port 2. And similarly, port 3 having some other function, receive data, transmit data, timers and counters, interrupts like this. So this is about the 8051 ports. And the next one is the interrupt, timer and serial port blocks. So here, coming to the timers and counters, so simply timers and counters are used to generate the timing signals or counting signals, and similarly to count the internal events or external events. So for that purpose, simply they can generate the delay values, that is timing action. Similarly, they can count the internal events or external events. So for that purpose, we are using timers and counters. So basically, we have two different timers are there, that is T0 and T1. So these two are completely 16-bit timers. So timer 0 is a 16-bit timer, as well as timer 1 is also 16-bit timer. So the same timer can be acting as a counter also to count the external events or any internal events. So here the T0 can be divided into two types, TH0, TL0. That is lower byte of T0 as well as higher byte of T0. The lower byte is 8 bits length. Similarly, higher byte is also 8 bit length. So both together can have 16 bit length of T0. So similarly, T1 also divided into two parts. That is TH1, that is higher byte of T1. Similarly, TL1, that is the lower byte of T1. So each having 8 bit length. So this is about the timers. And coming to the interrupts, basically the interrupts are nothing but the emergency talks or urgency talks. So whatever be the interrupt coming, based on the priority of the interrupt, simply the microcontroller can interrupt the main program and go to start the execution of the interrupt and come back to the main program. So this is about the interrupts. This can handle the urgent or emergency task. And next one is the serial port information. So simply serial port information, which is used for UART communication. So here to communicate with the external device, simply we can transfer the information serially. So here serial transformation means we can transfer the information bit by bit. That means we can transfer only one bit of data at a time. So after one bit, next bit can be transferred, so that we can transfer only bit by bit information with the external devices or external communication devices. So this is about the serial port information.